Hey everyone! Now that you've learned the basic rules about what logs allow us to do, I would like to take you through a few examples that show you the trickiness that can happen when you are trying to solve some of these problems. So let's jump right in and see what's going on, and I'm also going to make sure I mention the mistakes people usually make. Here we go. So this is the first problem. Looks very simple, right? It looks kind of like the things we did last week when we first learned about logs. And what most people want to do when they see, oh, there's e and there's a log, is they want to somehow cancel those out. But there's a problem. What do you do with the 4? I mean, does that become 4 times 5? Or does it become 4 plus 5? Or what? We don't know. And the problem is when you do canceling like that, you're actually breaking the rule. So let's remember exactly what the rule says. It says if you have a base and then right next to it you have a log of the same base, that's when you get to cancel them out, right? So those two cancel. But we don't have that situation here. There's a 4 in the way. And that 4 is causing us some trouble because it is keeping us from using our shortcut rule. The good news is this week we learned something about numbers that are out in front of logs. They're actually exponents, right? So the rule is that 4 actually belongs as an exponent on that 5. And I am allowed to move it up there because that's one of my rules, right? So if I move that up there, now we have 5 to the 4th. But the good news is we have e and natural log right next to each other now, which means I am allowed to cancel. My answer will just be 5 to the 4th, which is 625. So very common mistake people make. They know there's some rule about canceling and they just get a little carried away with their cancel. But this is the correct way to do a problem like this. Okay, now let's talk about taking several logs and condensing them into one. And I've also included something in this problem that people often mess up. But the first thing I want to do before we talk about the error is talk about these numbers out front. So as we said in the last problem, numbers in front of logs are exponents, and they should be dealt with first. So the very first thing I will do is to rewrite this problem, but to put the exponents where they belong. So we have log 3 minus log x squared plus, now that log to the 1/3, I could write it that way, or I could remember that a 1/3 exponent is actually a cube root. And then finally, we have minus log of z to the 4th. So if there are numbers in front of logs, kind of make that your habit to deal with them first. Okay, so this is the mistake people often make. They start at the beginning and say, okay, well, I know I have to write this as a single log, so I will write log here out front. And then I've got 3. And then, oh, subtracting means divide, so I'll divide by x squared. Oh, and then I'm adding, so I'll multiply by cube root y. And wait, then I'm dividing again? And we get weird answers that look kind of like that. So that's a problem because that isn't really the right answer. And number 2, it's kind of a mess, right? We've got things going all over the place. So how do we deal with this problem in a way that gives us a nice, organized answer that makes sense? So here's what I want us to know. When you have positive terms, like those two, they are multiplied, yes, and those values, the 3 and the cube root y, they will be in your numerator. However, these two terms that I'm underlining in red are subtracted. So instead of thinking I need to divide, which you will be, think of it this way. Subtracted terms will end up in the denominator of your fraction. So it really doesn't matter what order things are presented. Positive terms go on top, negative terms go on the bottom. So when I write my answer, I will write log one time only out front. Anything that's positive will go on top. So the 3 and the cube root y, they go on top. Anything subtracted goes on the bottom. So x squared and z to the fourth go on the bottom. And I also want to point out, it says single log. So another mistake sometimes I see people making is they have the right idea, but they write it this way. Log 3 cube root y over log x squared z to the fourth. See what the problem is? That's not a single log in blue. That's 2 logs. So that is not correct. We're going to X that out. The correct answer is in green. A single log with positive terms on top, negative terms on the bottom. So now let's take a look at another problem very similar to the first one, but definitely more complicated. So what we remember from before is that it's very tempting to want to cancel the 10 and the log, but now we really can't do that because what about this guy over here? Does he just get left out? What happens to him? So let's think about this problem again and think about what we can do that's legal math to simplify this. So we know the rule is if you have a base and you have a log that matches it, that's when you get to do the cancel, right? But if you don't have that situation, you can't cancel. And we don't have that situation. So I wonder if maybe we could use what we've learned this week to simplify that exponent. For example, right away I see there are numbers in front of logs. And as we have learned in both of the last 2 problems, those are exponents. So I am going to move those up. So I have log of 2 to the third plus log of 3 to the second. So that helps a little bit. Now another rule that we learned this week is when you have logs that are added, that means multiply, right? Logs that are added mean multiply. So I could actually combine these 2 logs into 1 log, and it would be the log of 2 to the third times 3 to the second. Now we're at a place where we have the setup we want. We have the 10 and we have the log base 10 right next to each other. They can cancel out, which leaves me 2 to the third times 3 squared, or 8 times 9, which is 72. So once you get the idea of how these problems can work and how our log rules work for us, they're not that hard to do. But we need to be careful of those illegal things that we're always tempted to do that would get us a wrong answer. So we talked in 2 problems ago about taking many logs and condensing them into 1. But what if you have 1 log and you want to spread it out into many? So what we have here is kind of a big mess, right? It is. But we want to spread this out into many logs. The first thing we should think about is how many logs will that be? So let's think about this. So I see a 64 and an x, and a lot of times people would say, oh, that's just 1 log. It actually is 2 because 64 and x are multiplied. So each one of those will be its own log. The y to the third and the z to the second, they will each be their own log. So I now know there are going to be 4 logs in my answer. So that's kind of a good place to start. Now the second thing I'd like to take a look at is this 5th root. That's kind of trapping all of those terms in it, right? And I can't do any splitting up until that 1/5 or that 5th root is dealt with. I kind of just gave it away. So what we need to do is think of that 1/5 or that 5th root, sorry, as an exponent, which is, of course, as I've said it twice now, 1/5. So we have 64x over y to the third z squared. I'm going to think of that whole thing to the 1/5 power. Why am I doing that? Well, because as you probably noticed, when there is an exponent happening, my first step is to deal with it. And in this case, instead of moving that exponent up, I'm going to move it back down. So everything I have in my answer will be multiplied by 1/5. And what that has done is just removed that radical from my fraction. So now I can deal with those 4 separate things. Okay, so remember what we said 2 problems ago. When things are in the numerator, those will create positive logs. And when they're in the denominator, they will create negative logs. So let's use that rule here. So our first one is 64. So we'll write log base 4, 64. The x is also in the numerator, so it will be positive. Log base 4x. Now the next 2 are both in the denominator. That means they're both subtracted. So minus log base 4, y to the 3rd, minus log base 4, z squared. Now sometimes people say, yeah, but the x or the y and the z are actually multiplied, right? Why wouldn't we add them? And yes, it's true they are, but if you were to add the log y and log z, you would need to put parentheses around the 2 of them to show that they are grouped in the denominator. So I usually just write them separately as subtracted logs. Okay, we have now taken a single log and written it as 4. Are we finished? Well, no, we're not, because I'm noticing we have some exponents here that can be brought down front, so I do need to do that. There's another thing I need to do, and that is right here at the beginning. Log base 4 of 64, that is a log value we should all just know. Because remember what that means, 4 to some power is 64. That's what we did last week. If you have a log that is an obvious one like this that you should know without a calculator, you need to evaluate it. So that means log base 464 will become 3 because 4 to the 3 is 64. The log x, we can't do much with that, so that's just going to stay there. For the log y, we'll bring 3 down front. And for the log z, we'll bring 2 down front. And now we have completely expanded this expression. So lots of little tricky things that can happen in there. For example, the subtraction signs, and then also forgetting that you actually know some log values, and if you do, you should definitely simplify. Okay, last question I'd like to talk about, and this kind of refers back to last week, but now we can talk about it in light of the rules that we know. So I want to talk about this function, this f of x equals log of x squared. And I want to compare it to what is actually an equivalent version of it, but when we're talking graphically, it is not. And I want to talk about this. And some of you have seen these functions already. Now, as we know, what happened here is a legal thing. We took that 2 and brought it down front. But is that okay to do when you're graphing? Do you get the same result? And the answer is you don't. So when you are given a function and asked to graph it, don't make any changes to it. You'll see why in just a second. So if I graph log x squared, what I will see is my normal log graph, but I will also see a mirror image of that log graph. Why does that happen? Well, let's think about this. If you pick an x value, normally with logs, you need a positive value, right? And if you do take a positive value, you will plug it in and get the right side of this graph. But in this problem, if I take a negative x value, which normally isn't even allowed, but if I do, immediately what happens is I square it and make it positive. So negative values are now okay in this function because I'm squaring them before I take the log. And that's why there is a graph on the negative side of the y-axis, because negative x values are allowed. And the graph ends up looking just like the right side, but a mirror image. Now, if I put this function, the g of x, in my calculator, all I see is that graph. So that is a log graph with a vertical stretch. Why don't they look the same when algebraically they are equivalent? Well, that's true, they are, but in the g of x function, I am not allowed to put negatives in for x, because the first thing that happens is I'm going to take the log of it, and you can't take the log of a negative. So a message to remember is when you are given a function and asked to graph it, don't make changes to it, because sometimes you may completely change what the function is and how many solutions it has. Notice that f of x has 2 solutions because it has 2 x-intercepts, whereas g of x only has 1. That's a big difference. So that's something we need to think about when we're solving later this week and also when we're graphing. How much should you simplify and what effect does it have? So hopefully these problems have given you some insight into the mistakes that I often see people make, and hopefully you will be so much smarter and not make any of them. Have a good one, everyone.